Welcome back, students, for lesson 17, which is properties of exponents and radicals. In this lesson, we are going to be applying the rules of exponents, simplifying exponential equations and expressions, just expressions, evaluate radical expressions, and use rational exponents. So we actually have a lot to cover in this lesson, a lot of different properties that are going to be happening. So just going to rapid fire them at you. All right, and the application we're building up to is your local hardware store sells ladders in 8, 16, and 24-foot sizes. You need to reach a bedroom window that is located 12 feet above the ground, and the ladder purchased needs to be able to reach the window while having its base be at least 5 feet from the house. So we will use the Pythagorean theorem, a squared plus b squared equals c squared, to find which ladder is appropriately sized. And the reason this fits into here is because we're talking about radicals. And so the common, probably most common use of radicals is when you are solving for a side length, or usually the hypotenuse, of a right triangle. So you can see my little diagram. We have our ladder needs to reach the window. It needs to be 12 feet high and 5 feet from the wall. And so that produces this triangle you see on the right, where we have a side length of 5, a side length of 12, and there will be a right angle right here, which will allow us to use the Pythagorean theorem. So we'll come back to that one at the end, but first we need to learn a whole bunch of rules of exponents. All right, so first rule is the rule of negative exponents. Anything, any base right here to the power negative n, so a to the power negative n, is equivalent to 1 over a to the positive n. So if you have a negative exponent, what you can do is move it to the denominator and it becomes a positive exponent when it's down there. This rule also works in reverse. If you had a negative exponent in the denominator, you can move it to the top to make it a positive exponent. So for the first one here, we have 2 to the power negative 2. This is equivalent to 1 over 2 to the positive 2, where all you do is move that 2 to the negative 2 to the bottom, and it becomes 2 to the positive 2. Okay? If we look at number 2, 2 over 5 to the power negative 2, this could be written as 1 over 2 to the 2 over 5 to the power positive 2, where we take that 2/5 to the negative 2 and move it to the bottom, make it a positive. But this is going to simplify, right? If we square what's down there, we're going to get 4 over 25, and then if we multiply by the reciprocal of that fraction, we get 25 over 4. What I want you to notice here is that 25 over 4, hey, we ended up flipping the 2/5 upside down. So there's actually an easier thing we could have done here. When you have fractions inside, you can actually just flip the fraction upside down to make the exponent positive. So 2 over 5 to the power negative 2 is equivalent to 5 over 2 to the positive 2. A positive 2 right there. And so one way to use this rule is to flip what's inside the parentheses and then make the exponent positive. So I flip the 2 over 5 to be 5 over 2 and turn the negative 2 to be positive 2. Or you could think of it as take the 2/5 and put it in the denominator and then make the exponent positive. So real quick, let's see how number 1 looks the same as that. We had 2 to the power negative 2. Well, 2 to the negative 2 is really 2 over 1 to the power negative 2, where I just write 2 over 1 instead of 2. So if I flip that fraction upside down, that's 1/2 to the power negative 2. And, 1/2 to the power positive 2, because when I flip this upside down, the exponent changes signs. And then 1/2 to the positive 2, another rule we're going to see is that these exponent distributes. So this is 1 squared over 2 squared, which is just 1 over 2 squared. Okay, notice I'm not simplifying 2 squared right now, even though that's 4 and we know that's 4. I'm leaving it as 2 squared just so we can talk about the exponents specifically. So you can use this rule one of two ways. You can either move the 2 to the negative 2 to the denominator and make the 2 positive, or you can just flip 2 to be 1/2 and then make the exponent positive that way. All right, product rule is next. When you have two things that have the same base, so a and a are bases, raised to exponents, and you multiply them together, you add the exponents. So it's called the product rule because we're multiplying two things with exponents, and when we do that, we add the exponents. So when we want to simplify 9x to the 4th times 4x to the 5th, We can multiply the 9 and the 4 because those come to the front using the commutative property to give us 36. And this x to the 4 times x to the 5th, we just add those exponents together to put them together. So this is x to the 9th. Okay, so we use the commutative property of multiplication to take the 9 and the 4 and move it to the front. And then once we have the x to the 4th and x to the 5th next to each other, this product rule allows us to add those exponents because they have the same base, x and x. Okay, for the next one, same idea. We're going to take all the coefficients, move them to the front using the commutative property. So 8 times 2 times 5, well, 2 times 5 is 10, times 8 is 80. And then we're just going to add all the exponents on the z's. So when I add together 6, 9, and 3, okay, my new variable is going to be z to the 6 plus 9 plus 3. Okay, when you add these together, that is 18. So we have 80 z to the 18. Okay, so the commutative property allows us to put the numbers in front and the variables in back, and the product rule allows us to add together those exponents. The quotient rule, very similar. When you have two things with the same base, a over a, so a is the base of both, m and n are our exponents. When we divide a to the m by a to the n, we subtract those exponents. And this is actually just a combination of the two previous rules we've seen. Okay, so I'm going to show you why with this first one here. So if we use the quotient rule on this first one, we would do y to the 17 minus 5, which is y to the 12. But let me show you how we can use the rule of negative exponents to combine this with the product rule and get the quotient rule. Y to the 17 over y to the 5 is equivalent to y to the 17, y to the negative 5. Because when you have this on bottom, this y to the 5 on bottom, you can move it to the top by making its exponent negative instead. So just like before, we could move y to the negative 5 to the bottom and make it y to the positive 5. It also works in reverse. We can move it to the top. And then now the quotient rule, gosh, the product rule, can't talk in this video apparently. The product rule allows us to add together y to the 17 and y to the negative 5 is y to the 17 plus negative 5. We add those exponents and we get y to the 12, which notice is the same answer we had above. But we don't want to have to move this y to the 5 up and then add them together. We would much rather just subtract them from the beginning because we know this 5 will become negative when it comes up. So we can just do subtraction from the beginning. All right, for the next one, we have x to the 34, y to the 45 over x to the 12, y to the 14. If we focus on just the x's first, we have x to the 34 minus 12. And then for the y's, we have y to the 45 minus 14. Okay, if we simplify each of those, 34 minus 12 gives us x to the 22, and 45 minus 14 gives us y to the 31. Right, so we can easily just subtract the exponents on the x's and subtract the exponents on the y's when we are dividing. Okay, next one, number 7, the zero exponent property. We have that anything to the power 0 equals 1. So a to the power 0 is 1 no matter what a is. All right, unless a is 0. But that's we don't talk about that case. Just kidding. 0 to the power 0, not covered in this class. But if it's anything else to the power 0, then we're going to get 1 here. And we actually have a good reason for that. Let's say we use the quotient rule to simplify x cubed over x cubed. Well, x cubed over x cubed is x to the 3 minus 3 based on the quotient rule, which is x to the 0. So how do I know that this is 1? Well, let's just divide like normal. If I have something cubed over something cubed, that's 1, okay? Because I have this something over itself. When you divide something by itself, you get 1 every time. But using the quotient rule on this, we get x to the 3 minus 3, which is x to the 0. So therefore, by all these equalities, we have that 1 is equal to x to the 0. And notice we never said what x was, so this is true for all numbers. All right, so now, number 7, we're going to simplify. We have x to the 0, y to the 3, y to the negative 3. X to the 0 right here is automatically 1. And then y to the 3 times y to the negative 3 is y to the 3 plus negative 3. So this equals 1, let me change that back to blue, 1 times y to the 0, but y to the 0 is also just 1, so this just equals 1. Okay, so we have 1 times y to the 0, but y to the 0 is also 1, so the whole thing is 1. Number 8, we're going to combine two rules. We have 3 to the 0 over m to the negative 8. 3 to the 0 is 1, so we have 1 over m to the negative 8. And rule of negative exponents, if it's m to the negative 8 down here, we can move it to the top to make it m to the positive 8. So all we do is move that m to the negative 8 to the numerator, and we get a positive 8 as our new exponent when we move it up. Okay, the power rule of exponents allows us to distribute an exponent inside of parentheses. So if we have a to the m to the power n, we multiply this n times whatever exponent is inside. So we get m times n as our new exponent. So for number 9 here, we have z cubed to the power 6. This is equal to z to the power 3 times 6, which is z to the 18. So you just multiply the exponents in that case. For number 10, nothing else different. X to the 12 to the power 4. We multiply 12 times 4 as our exponent, and we get x to the power 48. The power of a product rule, very, very closely related, it just allows us to distribute this exponent to both things inside. So if we have a times b on the inside and an exponent of m, we multiply that m by both things that are on the inside. So we'll end up with a to the m times b to the m, where again that m goes to both things inside. Please remember that this is a product inside. So if it was a plus b to the power m, this does not equal a to the m plus b to the m. Okay, this rule does not hold true when it is addition inside. Okay, so again, this is not true. Okay, not an accurate statement. But when it's a product inside, a times b, then we distribute the m to both things. So down here for number 11, we have 4z to the 17 to the power 3. This is going to be equal to 4 to the 3 times z to the 17 times 3. Okay, 4 to the 3 is 4 times 4 times 4. That's 64. And z to the 17 times 3, if you play darts, you're good at multiplying by 3s, hopefully. 17 times 3 is 51. If you don't get that reference, please play some darts. It's a very fun game, very inexpensive, and helps you practice multiplying and adding numbers together. All right, number 12, we got to do a little bit of simplification here. On the top, we have to distribute this exponent of 6 to all three exponents on the inside. And on the bottom, we have to do the same thing with the exponent of 5 to all three things on the inside. We zoom in here real quick. I want you to realize on the z down here in the bottom, the exponent is 1. We just don't write the 1 because z to the power 1, we never write that 1 there. Okay, so just be careful. There is a 1 as the exponent there, so we have to multiply 5 times 1. Okay, on the top, x cubed to the power 6 is x to the 18. Y cubed to the power 6 is y to the 18. Z to the 5th to the power 6 is z to the 30, where I'm just multiplying 6 times all those exponents inside. Then in the denominator, we're multiplying all the exponents times 5. So we get x to the 25, y to the 15, and z to the 5. Or again, I get this 5 here because it was z to the 1, and then I multiply by that 5 on the outside. Okay, so now we have exponents on top and bottom. We have to now use the quotient rule to simplify. And this is a case of the quotient rule we didn't cover earlier because I was saving it for number 12 down here, where every other time we've done this, so when we were doing the quotient rule earlier, we would do x to the 18 over x to the 25 gives us x to the 18 minus 25. But notice that if I write that down, x to the 18 minus 25, that's x to the negative 7. Right? And we don't want x to the negative 7 because we want to end with positive exponents. Okay, we should have all positive exponents by the end of this. So instead of going that direction, okay, instead of moving these 25x's to the top and making them negative, let's move these 18x's down. All right, and the idea here is whichever exponent is bigger between 18 and 25, we want to leave the big one where it is and move the small one towards the big one. So since x to the 25 is bigger than x to the 18, we're going to move the x to the 18 to the bottom. So when we write our new fraction, instead of doing x to the 18 minus 25 on top, I'm going to do x to the 25 minus 18 in the denominator. Okay, for the y variables though, I have 18 on top and 15 on bottom. Since 18 is bigger, I want to move the y to the 15 up. So I'll end up with y to the 18 minus 15 on top, because again, I move the y to the 15 up and it becomes negative 15 as my new exponent. For the z's, I have 30 on top and 5 on bottom, so I'm going to move the z to the 5 up, and I'll do z to the 30 minus 5 on top. So again, we're just trying to keep the exponents positive, so you move it in the direction that results in a positive exponent. All right, when we get this all simplified, we have y cubed, z to the power 25, and in the denominator, x to the power 7, where notice all my exponents at the end are positive because I made good decisions as far as which way to move my variables. Okay, next one is power to a quotient property. We've actually seen this earlier in the video. I showed it to you before we actually learned it, where when we have a quotient, aka a fraction inside, and an exponent, we distribute this exponent to both the numerator and denominator. So earlier in the video, I had 5 over 2 squared, and I told you this was 25 over 4. Okay, the reason we get that is we square the top to get 25, and we square the bottom to get 4. So when we do that with variables, all we do is multiply this exponent on the outside times the exponent in the numerator and whatever exponent is in the denominator. So for number 13 here, z to the 4 over 5 to the power 4 becomes z to the 16, because 4 times 4, over 5 to the power 4. Where I multiply 5 has an exponent of 1, that 1 gets multiplied by 4. All right, and 5 to the 4, pretty big number. 5 times 5 is 25, times 5 again is 125, times 1 more 5 is 625. So we end up with z to the 16 over 625. Okay, number 14 is just meant to scare you. I have a 0.5 on the outside. Ooh, scary, but we know how to multiply by decimals. So no big deal. We can distribute this 0.5 to all three things on top and to all three things on bottom. And this is no issue for us, okay? We just multiply by 0.5. We could also think of it as 1/2 if we prefer fractions to decimals. Either way. On top. Hey, wait a second. Am I working too hard here, guys? So hopefully you think the answer is yes, because you guys are smart. You looked at this original problem and said, whoa, 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 Mr. K, why would we distribute it to the top and the bottom when we could simplify the inside first? And I think you're right. So we could do what I was about to suggest, which is distribute this 0.5 to all three things on top and all three things on bottom, but we can actually make it easier on ourselves. Okay, we can simplify the top and bottom first, meaning the inside of these parentheses, we can simplify first, and then we could distribute the 0.5. So let's try that. Okay, if we leave these parentheses and the 0.5 on the outside, on the inside, we have x to the 7 over x to the 5. That's x squared, because 7 minus 5. Y to the 7 over y cubed is y to the 4, because 7 minus 3. And z to the 5 over z is z to the power 4, because 5 minus 1. So now if we distribute this 0.5 to all three things inside, x squared, if we multiply the 2 times 0.5, we just get 1. Y to the 4, 4 times 0.5 is 2. And again, z to the 4, 4 times 0.5 is 2. So this all simplifies to just be x, y squared, z squared. Where I recommend you try to distribute the 0.5 to all the tops and all the bottoms and then simplify and see that you get the same result no matter what order you do it in. But this one was here to show you that sometimes it's easier to simplify things before distributing. Okay, so sometimes you distribute first, everywhere on top, everywhere on bottom, but sometimes it's better to simplify the inside first and then do that distribution. All right, number 15, we're on to simplifying exponential expressions. So now this is just a matter of distributing and rearranging. Okay, so we're combining a couple rules we had. First things first, you want to deal with exponents that are on the outside. So for number 15, we have this square on the outside over here. We're going to distribute that to all three places inside. So the first set of parentheses I'll leave alone. Negative 2a cubed b to the negative 1. But that second set of parentheses is going to become 5 squared is 25. A to the negative 2 squared is a to the negative 4. And b squared squared is b to the 4. Because we're just multiplying those exponents by the 2 on the outside. Now if we put things together, the negative 2 and the 25 give me negative 50. A to the power 3 times a to the power negative 4 is a to the negative 1. And b to the negative 1 times b to the 4, we add those to get b to the 3. We can't leave our answer like this though. We need all positive exponents at the end. So we're going to put that a to the negative 1 on bottom and leave the negative 50b cubed on top. So notice all I did in this last step was take this a to the negative 1 and move it to the denominator to make it a to the positive 1, where we don't write that positive 1 because a to the 1 looks better when we just write a. All right, number 16. We're in another situation where we have a fraction on the inside and an exponent on the outside. So it's up to us what we want to do first. We can either simplify this inside first or distribute this exponent out here first. In this case, it looks like it might be a little bit easier to simplify the inside first, so we're going to go ahead and try that. So in the numerator here, we have to distribute this 4 on the outside to all three things inside these parentheses up top. So if I do that, 2 to the power 4 is 16, x squared to the power 4 is x to the 8th, and y to the power 4 is just y to the 4. In the denominator, I have a 2 on the outside that I have to distribute to all the things inside. So 7 squared is 49, x to the negative 1 squared is x to the negative 2, and y squared squared is y to the 4. All right, now the inside's going to simplify to be not too bad, because we have 16 over 49, which actually doesn't really simplify much at all, because 16 is 4 times 4, 49 is 7 times 7. Like, we can't really get a whole lot out of that. Okay, no real factors in common there. But x to the 8th and x to the negative 2 simplifies nicely. If I move this x to the negative 2 to the top, it becomes x to the positive 2. And then x to the 8th times x to the positive 2 is going to give me x to the 10th on top. Okay, so I'm trying to simplify the inside of this set of parentheses. So 16 and 49 stayed put, but x to the 8th over x to the negative 2 becomes x to the 10 on top. And for the y's, we have y to the 4 over y to the 4. Well, this is y to the 4 over itself, so these just cancel. But the way you can see that cancellation happen is this y to the 4 down here, if we move it to the top, it becomes y to the negative 4, and then y to the 4 times y to the negative 4 just gives us y to the 0, which is just 1. So I'm saying that they cancel, but really y to the 4 over y to the 4 equals 1, so I could write times 1 in my new expression, but there's just no need. So instead we just leave out those y's. All right, so now we have some real big ugly numbers, okay? Because we have to now distribute this cube on the outside. And so what we're going to do is distribute that 3 to the 16 to get 16 to the power 3, and distribute that 3 to the x to the 10 to get x to the 30, and distribute that 3 to the 49 to get 49 to the power 3. Now, I don't know about you, but I don't know what 16 cubed or 49 cubed is. So I'm going to pull out a calculator and see if we can simplify that nicely, but it's really not going to look any better when we do it. So I'm going to show you what it looks like, but really we're just going to end up leaving it like this. 16 cubed x to the 30 over 49 cubed. So if I tried it, fraction 16 to the power 3 over 49 to the power 3. You see how big and ridiculous those numbers are? So although we could write it as 4,096 over 117,649, I think our answer looks a whole lot better if we leave it as is, which is 16 cubed over 49 cubed. All right, so now we're about to switch into radicals, so I'm going to put that one in a separate video. Okay, so go ahead, watch part 2 coming up later.